Tonight, as you get ready to sleep, we'll clearly explain what school didn't cover about the gas giants, how their gravity shapes orbits, how their magnetic fields affect the space around them, and why that matters for Earth. You can relax and learn at the same time, fall asleep knowing you understood something new without effort. Tonight, we're not going to talk about Mars or the Moon or even the rocky ground beneath our feet. Instead, we're going to drift much farther out, past the familiar inner planets, past the asteroid belt, into a realm of the solar system that doesn't play by the rules we know. We're going to the gas giants, those colossal worlds that hang in the outer darkness like lanterns made of cloud and storm and mystery. Jupiter, Saturn, Uranus, Neptune. You've heard their names, seen their pictures in textbooks, maybe even glimpsed them through a telescope if you've been lucky. But what school taught you about them was often just the surface, the basic facts, the numbers that fit neatly into a test. What they didn't tell you, what they couldn't tell you in the time they had, was what these worlds actually are. Not just planets, but entire universes unto themselves, each one strange enough to rewrite what you thought possible, each one carrying secrets that we're only beginning to understand. These are not worlds you could ever stand on. There's no ground to catch you, no solid surface waiting beneath the clouds. If you fell into one, you would keep falling through layers of atmosphere so thick they would crush you long before you found anything resembling a floor. And yet, despite this, or perhaps because of it, the gas giants are among the most fascinating places in our solar system. They are laboratories of extreme physics, factories of weather beyond imagination, and hosts to moons that might harbour life in oceans hidden beneath ice. They shaped the early solar system, flinging rocks and water inward, sculpting the orbits of everything around them. They protect us still, their immense gravity fields sweeping up asteroids and comets that might otherwise find their way to Earth. In a very real sense, we owe our existence to these distant giants. Without them, the story of life on our small blue world might never have been written. Before we go any further, before we begin this long, slow journey into the outer solar system, I'd like to know something. Where are you right now? What time is it where you are? Are you lying in bed, the room dark around you, or are you somewhere else, letting your mind wander as the day fades? It's a strange thing, isn't it, that no matter where you are, no matter what time it is, we can share this moment. You listening to these words, and me speaking them into the quiet. And together, we're about to travel billions of kilometers without moving at all. If this kind of journey appeals to you, if you like the idea of drifting through space and time at the pace of a bedtime story, I'd be grateful if you considered subscribing or leaving a like. It's a small thing, but it helps this quiet voice reach others who might be searching for the same kind of wonder. So settle in now, let your breathing slow, let the weight of the day begin to fade. We have a long way to go tonight, and there's no need to hurry. The gas giants have been out there for more than 4 billion years. They'll wait for us. We're going to take our time, moving gently from one world to the next, exploring not just what these planets are, but what they mean, what they tell us about the universe, about formation and chaos and beauty in places no human eye has ever directly seen. We'll walk, in a manner of speaking, across moons where volcanoes erupt not with lava but with ice, where geysers shoot into space, where underground oceans might be stirring with life. We'll drift through storms larger than our entire planet, storms that have raged for centuries without end. We'll look at rings that shimmer in the sunlight, delicate and impossibly vast, made of billions of pieces of ice, each one catching the distant glow of the sun. But first, we need to understand what a gas giant actually is, because the name itself is a little misleading. When we call them gas giants, it sounds like they might be nothing but air, vast bubbles of atmosphere floating in space. But that's not quite right. These planets have structure, layers, depth. They're more like onions than balloons, with each layer distinct from the one above and below. At their cores, buried beneath thousands of kilometers of crushing atmosphere, there may be something solid after all, a heart of rock and metal, compressed under pressures we can barely imagine. Above that core, if it exists, the materials that make up the planet are squeezed so tightly that they stop behaving like gases altogether. Hydrogen, the most common element in these worlds, becomes something strange under such conditions. It becomes metallic, a state of matter that doesn't exist naturally anywhere on Earth. In this form, hydrogen conducts electricity, flows like liquid metal, and generates the powerful magnetic fields that wrap around these planets like invisible shields. Higher up, in the layers we can actually see, the atmosphere is more recognizable, though no less alien. Clouds of ammonia, methane, water vapor, and other compounds swirl in bands and storms, driven by heat rising from below and by the planet's rapid rotation. These are not the gentle clouds of Earth. They are rivers of gas moving at hundreds of kilometers per hour, systems so large that our entire planet could be swallowed by a single storm. The colors we see in images of Jupiter and Saturn, those beautiful bands of cream and brown and red, are the result of complex chemistry, of molecules breaking apart and recombining under the glare of ultraviolet light, of materials dredging up from deeper layers and painting the upper atmosphere in shades we're still learning to interpret. And then there are the moons. Oh, the moons. If the gas giants themselves are strange, their moons are stranger still. Jupiter alone has dozens, from tiny captured asteroids to worlds larger than the planet Mercury. Some of these moons are geologically active, their surfaces constantly reshaped by forces we didn't even know existed until we sent probes to look. Others are frozen and ancient, their faces scarred by billions of years of impacts, records of violence written in ice and rock. A few, just a few, show signs that beneath their frozen crusts there are oceans. Liquid water kept warm by tidal forces, by the gravitational pull and push of the giant planet they orbit. And where there is liquid water, where there is energy and chemistry, there might be life. Not little green men, not cities or civilizations, but something simpler, something microbial perhaps, yet no less profound. The possibility alone is enough to make these moons some of the most important places in the solar system. So that's where we're going tonight. Out past Mars, where the sunlight grows dim and the distances become almost unimaginable. Out to where the planets don't have surfaces, where storms last for centuries, where moons eclipse their parents in slow, stately dances that have repeated since the solar system was young, out to the gas giants to see what school never quite had time to teach you. Not just the facts, though we'll cover those too, but the feeling of these places, the sense of scale and strangeness and beauty that can only come from taking the time to really look, to really imagine what it would be like to be there, drifting in the darkness, watching these vast worlds turn. The journey to the outer solar system is not a quick one. If you were to board a spacecraft today and point it toward Jupiter, the closest of the gas giants, it would take years to arrive even with our fastest rockets. The distances involved are so large that light itself, which can circle the Earth more than 7 times in a single second, takes more than 40 minutes to travel from the Sun to Jupiter. By the time it reaches Neptune, the farthest of the 4 giants, nearly 4.5 hours have passed. This is a realm of space where the sun, that blazing furnace that dominates our sky, appears as little more than a bright star, its warmth so diminished that the surfaces of these worlds are frozen to temperatures that would shatter steel. Yet despite the cold and the distance, these planets are not lifeless or inert. They are churning, dynamic systems, each one generating more heat than it receives from the sun. This internal heat, left over from their formation and sustained by the slow contraction of their massive interiors, drives weather systems of almost unimaginable power. Winds scream across their cloud tops at speeds that would tear apart any structure we could build. Storms the size of Earth form and persist, some for mere decades, others for centuries. Lightning bolts, far more powerful than any seen on our world, flash in the depths of their atmospheres, illuminating clouds from within. Understanding these giants required patience and ingenuity. For most of human history, they were nothing more than wandering lights in the sky, mysterious and unreachable. Ancient astronomers tracked their movements, noting how they drifted against the fixed stars, how they sometimes seemed to stop and reverse course, retrograde motion caused by the geometry of orbits. But it wasn't until the invention of the telescope that these lights resolved into worlds. Galileo, in the early 17th century, pointed his crude instrument at Jupiter and saw not just a disk, but 4 small points of light arrayed around it, moons that orbited the planet just as our moon orbits Earth. It was a revelation, proof that not everything in the cosmos revolved around us. Over the centuries, telescopes improved, and the gas giants slowly gave up their secrets. Astronomers mapped the cloud bands of Jupiter, watched as the great red spot drifted across its face, measured the stunning rings of Saturn, and discovered moon after moon circling these distant worlds. But it was only in the late 20th century, with the advent of space exploration, that we truly began to understand what these planets were. The Pioneer and Voyager missions, those tiny robotic emissaries we sent into the darkness, transformed the gas giants from distant mysteries into real places, worlds with weather and geology and stories written in ice and stone. The images they sent back were nothing short of miraculous. Jupiter, no longer a fuzzy disk, but a roiling cauldron of storms and currents, its atmosphere alive with motion. Saturn, its rings revealed in astonishing detail, thousands of individual ringlets nested within each other like grooves on a cosmic record. Uranus and Neptune, the ice giants, each with their own strange beauty, their blue-green hues the result of methane in their atmospheres absorbing red light and reflecting back only the cool tones of the spectrum. And the moons, oh the moons, Io painted in sulphur and volcanic flows. Europa, its surface a cracked shell of ice hiding an ocean below. Titan, wrapped in a thick orange haze, its surface hidden but tantalizingly complex. Triton, captured and tortured by Neptune's gravity, erupting with geysers of nitrogen ice. These discoveries reshaped our understanding of what a planet could be, of what was possible in the universe. They taught us that the solar system was far stranger, far more diverse than anyone had imagined. They showed us that even in the frozen outer reaches, far from the sun's warmth, there was beauty and complexity and maybe, just maybe, the ingredients for life. And yet, for all we've learned, there is still so much we don't know. The gas giants guard their secrets well, hidden beneath layers of cloud and distance. Every mission reveals new mysteries, new questions that demand answers. What lies at the very center of Jupiter? How did Saturn's rings really form? Why is Uranus tipped on its side? What powers the furious winds of Neptune? These are the questions we'll explore as we drift through this long night, moving from world to world, moon to moon, letting the strangeness and scale of these places wash over us. There's no test at the end, no need to remember every detail. This is a journey for its own sake, a chance to see the solar system not as a list of facts, but as a collection of worlds, each one as real as the ground beneath your feet, each one waiting in the darkness, turning slowly under the distant gaze of the sun. So take a breath. Let yourself relax. We're about to begin in earnest, starting with the largest, the most massive, the king of planets. We're going to Jupiter, that swirling giant whose gravity holds dozens of moons in its grip, whose storms have raged since before humans walked the Earth, whose very presence shaped the solar system into the form we see today. Jupiter is where our story truly begins, and it's waiting for us, hanging in the void, patient and vast. Jupiter is not a planet in the way you might imagine a planet to be. It doesn't have a surface you could land on, no solid ground hidden beneath the clouds waiting to catch a spacecraft or an explorer. If you tried to descend into Jupiter, you would simply fall, dropping through layer after layer of atmosphere, each one thicker and hotter than the last, until the pressure became so great that the distinction between gas and liquid disappeared entirely, and you found yourself surrounded by something that was neither air nor ocean, but something in between. Long before that point, of course, you would have been crushed and incinerated, your atoms scattered into the roiling currents of a world that doesn't care for visitors. But let's imagine, just for a moment, that you could survive such a journey. What would you see as you fell? At first, high above the cloud tops, you would be treated to a view unlike anything else in the solar system. Jupiter from above is a work of art painted in motion, bands of colour stretching across the planet in parallel lines, cream and brown and ochre, separated by dark belts where the atmosphere has sunk and cooled. These bands are not static, they flow, driven by the planet's rapid rotation. Jupiter spins faster than any other planet in the solar system, completing a full rotation in less than 10 hours, despite being more than 11 times wider than Earth. This furious spin flattens the planet slightly at the poles and throws the atmosphere into powerful jet streams that race around the planet at speeds exceeding 400 kilometers per hour. As you descended, you would begin to notice the storms. Everywhere, at every scale, the atmosphere is in motion. There are ovals, white and brown and red, swirling like cosmic whirlpools. There are long streaks where different jet streams meet and interact, creating turbulence that can persist for decades. And then, of course, there is the Great Red Spot, that most famous of all Jovian features, a storm so large that 2 or 3 Earths could fit inside it with room to spare. The Great Red Spot is not a hurricane in the way we understand hurricanes on Earth. It's an anticyclone, a high-pressure system that rotates in the opposite direction to the surrounding flow. It has been observed for at least 300 years, possibly longer, making it the oldest known storm in the solar system. Why it has persisted for so long is still not entirely understood. On Earth, storms like this would dissipate quickly, their energy sapped by friction with the ground or by cooler water. But Jupiter has no ground, and its internal heat keeps feeding energy into the atmosphere from below. Recent observations suggest the Great Red Spot may be shrinking. Images from the late 1800s show it was much larger then, spanning a width that could swallow 3 Earths. Now, it's closer to 1 Earth across, and the rate of shrinking seems to be accelerating. Will it eventually disappear altogether, or will it reach some equilibrium and persist for another few centuries? We don't know. Jupiter keeps its own counsel, and we can only watch and wonder. Deeper into the atmosphere, the pressure and temperature would continue to climb. At a depth of perhaps 50 kilometers below the visible cloud tops, you would pass through the layer where water exists as vapor and ice crystals, forming clouds that we cannot see from above, but that are revealed in infrared images. Below that, the pressure would reach several times that of Earth's atmosphere, and the temperature would soar to hundreds of degrees. Here, ammonia and other compounds condense and evaporate in cycles, driving the convection currents that power Jupiter's weather. The clouds we see from above are just the outermost layer, the foam on an ocean of gas that extends thousands of kilometers down. Keep falling, and eventually the atmosphere would become so dense that it would start to feel less like air and more like an ocean. The hydrogen that makes up most of Jupiter's bulk would compress under its own weight, and at a depth of several thousand kilometers, something extraordinary would happen. The hydrogen would undergo a phase transition, shifting from molecular hydrogen, the stuff you might find in a balloon, to metallic hydrogen, a state of matter so exotic that it has only recently been produced in laboratories on Earth, and even then only for fleeting moments. In metallic hydrogen, the pressure is so intense that the electrons are stripped away from their atoms and move freely, like electrons in a metal. This gives the material its name, and it also gives it unusual properties. It conducts electricity, it reflects light. And in the case of Jupiter, it generates a magnetic field so powerful that it extends millions of kilometers into space, far beyond the orbits of the innermost moons. This magnetic field is one of Jupiter's defining features. It's not just strong, it's vast, and it traps charged particles from the solar wind, creating radiation belts that dwarf anything found around Earth. These radiation belts are so intense that they pose a hazard to spacecraft. Several of our probes have had their instruments damaged or degraded by the sheer amount of radiation in Jupiter's vicinity. For any future mission hoping to explore the Jovian system in detail, shielding against this radiation is one of the key challenges. Below the layer of metallic hydrogen, deeper still, there may be a core. This is one of the great unknowns about Jupiter. Does it have a solid center, a ball of rock and metal left over from the planet's formation? Or is the core diffuse, mixed into the surrounding layers by billions of years of convection and stirring? Recent data from the Juno spacecraft, which has been orbiting Jupiter since 2016, suggests that the core might be larger and more diffuse than previously thought, spread out over a significant fraction of the planet's interior rather than concentrated in a compact ball. If this is true, it tells us something important about how Jupiter formed and how it has evolved over time. Jupiter is often called a failed star, though that's not quite accurate. It's true that Jupiter is made mostly of hydrogen and helium, the same elements that make up stars. And it's true that if Jupiter were about 80 times more massive, the pressure and temperature at its core would be high enough to ignite nuclear fusion, and it would become a star in its own right, a small red dwarf perhaps, but a star nonetheless. But Jupiter is nowhere near that mass. It's not even close. It's the largest planet in the solar system by far, more massive than all the other planets combined, but it's still just a planet. It shines not by its own light, but by reflecting the light of the sun, though it does emit more energy than it receives, a faint glow generated by the slow contraction of its interior and the heat left over from its formation. Still, the comparison to a star is not entirely without merit. In some ways, Jupiter acts like a miniature solar system unto itself. It has more than 70 known moons, ranging from tiny captured asteroids only a few kilometers across to the 4 great Galilean moons, worlds in their own right, each one unique and fascinating. These moons orbit Jupiter in a complex dance, their paths governed by gravity and resonance, and their surfaces tell stories of geology and chemistry and forces we are only beginning to understand. Jupiter also plays a crucial role in the dynamics of the solar system. Its immense gravity influences the orbits of everything around it, from asteroids in the belt that lies between Mars and Jupiter to comets that swing in from the outer reaches of the solar system. Some scientists believe that without Jupiter, Earth might have been bombarded by far more asteroids and comets than it was, making the development of life much more difficult. Jupiter acts as a kind of cosmic shield, sweeping up or deflecting many of the objects that might otherwise find their way to the inner solar system. It's not perfect, of course. Some objects still get through, but the overall effect is significant, and it's one of the reasons why the search for life in other solar systems often focuses on systems that have a large planet in the outer regions, a Jupiter analogue that might perform the same protective role. Yet Jupiter is not entirely benign. Its gravity can also fling objects inward, sending comets and asteroids on trajectories that bring them dangerously close to Earth. The Shoemaker-Levy 9 comet, which famously collided with Jupiter in 1994, was a dramatic demonstration of this. The comet had been captured by Jupiter's gravity and torn apart by tidal forces, and the resulting fragments slammed into the planet's atmosphere over the course of several days, creating massive fireballs and leaving dark scars in the clouds that persisted for months. It was a vivid reminder of the power of gravity and the violence that can occur in the solar system. From Earth, Jupiter is often one of the brightest objects in the night sky, outshone only by Venus and, on rare occasions, Mars. It's easy to spot, a steady, unwavering point of light that doesn't twinkle like the stars do. Through even a small telescope, you can see its disk, and if you're patient, you can watch its moons slide in front of or behind the planet, their tiny shadows crossing the cloud tops. It's a view that hasn't changed much since Galileo first observed it more than 400 years ago, a reminder that some things in the universe are constant, or at least appear so on human timescales. But beneath that serene exterior, beneath the beautiful bands and the stately motion of the moons, Jupiter is a world of chaos and extremes. It's a planet where the weather never stops, where lightning bolts 1,000 times more powerful than those on Earth flash in the darkness, where auroras larger than our entire planet shimmer at the poles, fed by charged particles funneled down the magnetic field lines. It's a place where the rules are different, where the familiar physics of solid ground and breathable air give way to pressures and temperatures that defy easy comprehension, and it's a place that continues to surprise us. Every new mission reveals something unexpected. Juno, with its highly elliptical orbit that takes it skimming just above the cloud tops, has sent back images of Jupiter's poles, regions that had never been clearly seen before. Instead of the orderly bands that dominate the equatorial regions, the poles are a chaotic swirl of storms, dozens of cyclones packed together in geometric patterns that shift and evolve. Why they form these patterns, why they don't merge into one giant storm, is yet another mystery that scientists are working to understand. Jupiter is a reminder that even in our own solar system, even in a place we've been studying for centuries, there are still secrets waiting to be uncovered. It's a world that rewards patience and curiosity, a world that asks us to think beyond the familiar and to imagine what it would be like to live in a universe where planets can be made entirely of gas, where storms can rage for centuries, and where the ground beneath your feet is not a given but a luxury reserved for smaller, rockier worlds. We'll stay with Jupiter a bit longer because we haven't yet talked about its moons, those small worlds that orbit the giant, each one a story unto itself. But before we move on, take a moment to imagine Jupiter as it is right now, out there in the darkness, turning on its axis, its clouds swirling, its storms churning, its moons gliding silently around it. It's been there for more than 4 billion years, and it will be there for billions more, patient and vast, waiting for the next probe, the next telescope, the next curious mind to look up and wonder what secrets it still holds. If Jupiter is a king, then its moons are its court, a collection of worlds so varied and so strange that each one could fill a documentary of its own. There are dozens of them, more than 70 at last count, and the number keeps growing as our telescopes improve and we detect ever smaller objects in orbit around the giant planet. Most of these moons are tiny, irregular chunks of rock and ice, probably asteroids that wandered too close to Jupiter and were captured by its gravity. But 4 of them, the Galilean moons, are different. These are worlds in the truest sense, large enough to be planets in their own right if they orbited the Sun instead of Jupiter. Their names are Io, Europa, Ganymede, and Callisto, and each one is a universe unto itself. Let's start with Io, the innermost of the 4, because Io is like nothing else in the solar system. It's a world on fire, not metaphorically but almost literally. Io is the most volcanically active body we know of, its surface constantly reshaped by eruptions that spew sulfur and sulfur dioxide into space. There are hundreds of active volcanoes on Io, and at any given moment several of them are erupting. Some of these eruptions are so powerful that they launch material hundreds of kilometers above the surface, high enough that the plumes can be seen from space, glowing faintly in the darkness. The reason for this volcanic fury is tidal heating. Io orbits very close to Jupiter, and the gravitational pull of the giant planet is immense. But Io is also influenced by the other Galilean moons, particularly Europa and Ganymede, which pull on it from the outside. These competing gravitational forces stretch and squeeze Io like a rubber ball, and this constant flexing generates heat deep within the moon's interior. It's the same principle that makes a wire heat up if you bend it back and forth repeatedly, except on a planetary scale. The heat melts rock, creates magma, and drives the volcanic activity that gives Io its hellish landscape. From space, Io looks like a mouldy pizza, splotched with yellows, oranges, reds, and blacks, the colours of sulfur compounds in various forms. There are calderas, volcanic vents, lava flows, and plains covered in sulfur frost. There's no water on Io, at least not on the surface. Any water that might have once been there has long since been baked away by the relentless volcanic heat. The atmosphere, if you can call it that, is vanishingly thin, made mostly of sulfur dioxide gas vented by the volcanoes. It's not enough to breathe, not nearly, but it's enough to interact with Jupiter's magnetic field, creating a torus of charged particles that encircles Jupiter at Io's orbit, a glowing donut of plasma that can be detected from Earth. Standing on Io, if you could withstand the radiation and the heat and the lack of breathable air, would be like standing in a landscape of constant transformation. The ground beneath your feet would be young, geologically speaking, no more than a few million years old in most places, and in some areas brand new, formed just days or weeks ago by a recent eruption. You would see towering plumes on the horizon, fountains of gas and dust rising into the black sky. You would see rivers of molten rock flowing across the surface, glowing red and orange, their heat radiating outward. And above you, filling half the sky, would be Jupiter, massive and ever-present, its cloud bands slowly rotating, its storms drifting across its face. Now let's move outward, to Europa, a moon so different from Io that it's hard to believe they orbit the same planet. Where Io is fire, Europa is ice. Its surface a smooth shell of frozen water, crisscrossed with cracks and ridges that give it the appearance of a shattered windshield. Europa is one of the smoothest objects in the solar system, with very few craters, which tells us that its surface is young, constantly being resurfaced by some process. That process, scientists believe, is driven by an ocean of liquid water that exists beneath the ice, kept warm by the same tidal heating that powers Io's volcanoes, though to a much lesser degree. The idea of an ocean on Europa is one of the most tantalizing discoveries in planetary science. If the ocean is real, and almost all the evidence suggests that it is, then Europa has more liquid water than all of Earth's oceans combined. The ice shell is probably 10 to 15 kilometers thick, maybe thicker in some places, maybe thinner in others, and beneath it is an ocean that could be 100 kilometers deep. This ocean is not sitting in a frozen vacuum. It's in contact with a rocky seafloor, and where water meets rock, especially warm rock heated by tidal forces, you get chemistry. You get the conditions that, on Earth, support life. We don't know if there's life in Europa's ocean. We have no direct evidence, no smoking gun, but the possibility is real enough that Europa has become one of the top targets in the search for life beyond Earth. Future missions are being planned to fly close to Europa to sample the plumes of water vapor that may be erupting from cracks in the ice, to use radar to map the thickness of the ice shell, and eventually to land and drill down through the ice to reach the ocean below. It's an ambitious goal, fraught with technical challenges, but the potential payoff is enormous. If life exists in Europa's ocean, it would answer one of the most profound questions we can ask: are we alone? The surface of Europa is not a hospitable place. The temperature hovers around -160 degrees Celsius, cold enough to freeze carbon dioxide. The surface is bathed in intense radiation from Jupiter's magnetosphere, radiation that would sterilize anything living on the surface within hours. But beneath the ice, shielded from the radiation, warmed by tidal heating, the ocean might be a very different story. It might be dark, yes, without sunlight to power photosynthesis, but life on Earth has shown that it doesn't always need sunlight. There are ecosystems on the ocean floor, around hydrothermal vents, that thrive in complete darkness, powered by chemical energy instead. If similar vents exist on Europa's seafloor, they could support life in the same way. Next is Ganymede, the largest moon in the solar system, bigger even than the planet Mercury. Ganymede is a world of ice and rock, its surface a mix of dark, heavily cratered terrain and brighter, grooved regions that suggest tectonic activity in the distant past. Like Europa, Ganymede is thought to have a subsurface ocean, though it's buried deeper, beneath a thicker shell of ice and possibly even layers of high-pressure ice that form under the immense weight above. Ganymede is also the only moon in the solar system known to have its own magnetic field, a feature that suggests it has a liquid, metallic core, similar in some ways to Earth's core. The grooved terrain on Ganymede is particularly intriguing. These grooves are long, parallel ridges and valleys that cover much of the moon's brighter regions. They may have formed when the icy crust was stretched and fractured, possibly due to tidal heating or internal convection. In some ways, Ganymede is like a textbook in planetary geology, showing evidence of processes that have shaped not just moons, but planets throughout the solar system. It's a quiet world now, geologically speaking, its surface old and cold, but its past was clearly more active. Finally, there's Callisto, the outermost of the Galilean moons, and in many ways the most mysterious. Callisto is heavily cratered, its surface one of the oldest in the solar system, a record of billions of years of impacts. Unlike Io, Europa, and Ganymede, Callisto shows little sign of geological activity. It seems to be a ball of ice and rock that has remained largely unchanged since it formed. And yet, like the others, it too may have a subsurface ocean, detected through measurements of its magnetic field and how it responds to Jupiter's magnetosphere. Why Callisto has an ocean despite being so geologically dead is still a puzzle, but it adds to the growing realization that subsurface oceans may be common in the outer solar system, hidden beneath the icy shells of moons that, from the outside, look frozen and lifeless. These 4 moons, the Galilean moons, are just the largest and most famous of Jupiter's retinue. There are dozens of smaller moons, many of them captured asteroids with irregular shapes and chaotic orbits. Some orbit in the opposite direction to Jupiter's rotation, a clear sign that they were captured rather than formed alongside the planet. These small moons are interesting in their own right, offering clues about the early solar system and the population of objects that once filled the space between the planets. But it's the Galilean moons that capture the imagination, because they show us that moons can be just as complex and interesting as planets. They're not just dead rocks orbiting a larger body. They're worlds with weather, geology, and in some cases, possibly even life. They're places we could, in principle, explore, places where future missions could land and drill and search for answers to questions we've been asking since we first looked up at the stars. Jupiter's magnetosphere is another feature that deserves mention because it shapes the environment in which these moons exist. The magnetosphere is the region of space around Jupiter dominated by its magnetic field, and it's enormous, stretching millions of kilometers into space, far beyond the orbits of the Galilean moons. Within this magnetosphere, charged particles are trapped and accelerated, creating intense radiation belts that pose a hazard to both spacecraft and any potential life on the moon's surfaces. The interaction between the magnetosphere and the moons is complex. Io, in particular, feeds the magnetosphere with particles from its volcanoes, creating a glowing torus of plasma that encircles Jupiter. Europa and Ganymede, with their subsurface oceans, may generate induced magnetic fields as Jupiter's field sweeps past them, interacting with the salty, conductive water beneath their icy shells. All of this makes the Jovian system not just a collection of objects orbiting a planet, but a dynamic, interconnected system where each part influences the others. Jupiter's gravity shapes the orbits and heats the interiors of the moons. The moons feed particles into Jupiter's magnetosphere. The magnetosphere bathes the moons in radiation. It's a complex dance that has been going on for billions of years, and it's one of the reasons why studying Jupiter and its moons is so important. Understanding this system helps us understand how planetary systems work, how moons form and evolve, and where we might find life beyond Earth. As we prepare to leave Jupiter and move on to the next giant, take a moment to appreciate what we've seen. A planet so large that 1,000 Earths could fit inside it, an atmosphere of endless storms, a magnetic field that reaches across millions of kilometers, and moons, 4 incredible moons, each one a world unto itself, each one offering mysteries and possibilities that we're only beginning to explore. Jupiter is more than just a planet. It's a system, a family, a laboratory where the universe experiments with scale and complexity and beauty, and it's waiting out there, patient and vast, for us to come back and look closer. Leaving Jupiter behind, we drift farther outward through the darkness, moving past the orbits of its moons, away from the pull of its gravity, and deeper into the outer solar system. The Sun, already distant at Jupiter, grows even smaller now, its light weaker, its warmth negligible. We're heading to Saturn, the second largest planet in the solar system, and perhaps the most beautiful, at least by human standards. Saturn is the planet with the rings, those stunning bands of ice and rock that encircle the planet like a crown, shimmering faintly in the sunlight. Even in a small telescope, Saturn's rings are visible, and they've captivated anyone who's ever had the chance to see them. But as striking as they are from a distance, the rings are even more fascinating up close, and the story of how they formed, what they're made of, and why they exist at all is one of the great tales of planetary science. Before we get to the rings, let's talk about Saturn itself, the planet they orbit. Saturn is often described as Jupiter's smaller sibling, and in many ways, that's accurate. Like Jupiter, Saturn is a gas giant, made mostly of hydrogen and helium. Like Jupiter, it has a thick atmosphere with bands and storms, though they're less vivid, less colourful than Jupiter's. Like Jupiter, it has a large family of moons, dozens of them, ranging from tiny captured objects to Titan, a moon larger than the planet Mercury and one of the most intriguing places in the entire solar system. And like Jupiter, Saturn generates more heat than it receives from the Sun, glowing faintly with the warmth of its own slow contraction. But Saturn is also different in some important ways. It's less massive than Jupiter, though still enormous by any standard, and its lower density gives it a unique distinction. Saturn is the only planet in the solar system that could, in theory, float on water if you could find an ocean large enough. Its average density is less than that of water, a quirk of its composition and structure. This low density also means that Saturn is more oblate than Jupiter, more flattened at the poles and bulging at the equator, a result of its rapid rotation and the balance between gravity and centrifugal force. Saturn's atmosphere is calmer than Jupiter's, at least on the surface. The cloud bands are there, parallel lines stretching around the planet, but they're muted, softened by a layer of high-altitude haze that obscures the details below. This haze is made of ammonia ice crystals, tiny particles that scatter sunlight and give Saturn its pale, golden colour. Beneath this haze, the atmosphere is more active. There are storms, though they're rarer than on Jupiter. Every few decades, a massive storm erupts in Saturn's northern hemisphere, a disturbance so large that it can be seen from Earth, a bright spot that spreads out into a long circling band as the planet's winds carry it around the equator. These storms are known as Great White Spots, and they seem to occur roughly every Saturnian year, which is about 30 Earth years. Why they appear on this schedule is still a bit of a mystery, but it likely has to do with seasonal changes in the planet's atmosphere, driven by Saturn's tilt and its long orbit around the Sun. Deep beneath the clouds, Saturn's structure is probably similar to Jupiter's, layers of gas transitioning to liquid and then to metallic hydrogen under increasing pressure, possibly with a core of rock and ice at the very center. Like Jupiter, Saturn has a powerful magnetic field, though it's weaker and smaller in extent. This magnetic field traps charged particles and creates radiation belts, though they're not as intense as Jupiter's. The interaction between Saturn's magnetic field and its moons, particularly Enceladus and Titan adds complexity to the system in ways we're still working to understand. But let's be honest, when most people think of Saturn, they think of the rings. And rightly so, because the rings are extraordinary. From a distance, they look like solid disks, smooth and continuous, but they're not. They're made of countless individual particles, ranging in size from grains of sand to chunks as large as houses, each one orbiting Saturn independently, all of them locked in a delicate gravitational dance that has persisted for millions, perhaps billions of years. The rings are thin, astonishingly thin. If you could view them edge-on, they would almost disappear, a line barely visible against the blackness of space. In most places, the rings are only about 10 meters thick, and yet they stretch outward from the planet for hundreds of thousands of kilometers. The composition of the rings is mostly water ice, bright and reflective, which is why they shine so brilliantly in the sunlight. There's also some rocky material mixed in, dust and debris that darkens the ice in places, and complex organic molecules, tholins, that form when ultraviolet light from the sun breaks apart methane and other compounds, creating the faint reddish tint seen in some of the ring regions. The origin of Saturn's rings is still debated. One idea is that they're the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces, shredded into pieces that spread out into a disk. Another possibility is that the rings are leftover material from Saturn's formation, bits of ice and rock that never coalesced into a moon because they were too close to the planet. Recent evidence from the Cassini spacecraft, which spent 13 years studying Saturn before plunging into the planet's atmosphere in 2017, suggests that the rings might be relatively young, perhaps only a few 100 million years old, formed long after the planet itself. This idea comes from studying the rings' composition and brightness. The ice in the rings is very pure, almost pristine, with relatively little rocky material mixed in. If the rings were ancient, billions of years old, you would expect them to be darker, dirtier, contaminated by the constant bombardment of micrometeoroids from space. The fact that they're so bright suggests that they haven't been around long enough for that pollution to accumulate. If this is true, it means the rings are a temporary feature, at least on geological timescales. They won't last forever. Gradually, over tens or hundreds of millions of years, the ice particles will either fall into Saturn's atmosphere, pulled down by gravity and atmospheric drag, or they'll collide with each other and stick together, eventually forming new moons. Future astronomers, millions of years from now, might look at Saturn and see a planet with no rings at all, just a faint trace of dust where the rings once were. But for now, the rings are there, and they're glorious. They're divided into several main sections, labelled with letters in the order they were discovered, not in the order they appear. The A-ring, B-ring and C-ring are the most prominent, visible from Earth with a decent telescope. The B-ring is the brightest and most massive, containing the most material. The A-ring is just outside it, separated by a dark gap called the Cassini division, named after the astronomer who discovered it in the 17th century. The Cassini division looks empty from a distance, but it's not. It contains some material, just much less than the main rings, and it's maintained by gravitational resonances with Saturn's moons. Particles in the Cassini division are in orbital resonance with Mimas, one of Saturn's inner moons, and this resonance gradually clears out the gap-sweeping particles into other regions of the rings. Beyond the A-ring are the F-ring, G-ring and E-ring, each one fainter and more diffuse than the main rings. The F-ring is particularly interesting because it's narrow and complex, with braids and kinks caused by the gravitational influence of two small moons, Prometheus and Pandora, that orbit just inside and outside the ring. These moons are called shepherd moons because they herd the particles of the F-ring, keeping it confined to a narrow band. The E-ring is the largest and most diffuse of all, extending far beyond the main rings, and it's fed by material from Enceladus, one of Saturn's most remarkable moons, which we'll come to shortly. Close-up images from Cassini revealed that the rings are not smooth at all. They're full of structure, thousands of individual ringlets nested within each other, gaps and waves and spiral density patterns caused by the gravitational pull of Saturn's moons. Some of these features are called propellers, small gaps cleared by moonlets embedded in the rings, too small to be seen directly but large enough to push the surrounding particles aside. Other features are waves, spiral patterns that ripple outward through the rings, caused by resonances or by collisions with small objects. The rings are not static, they're constantly evolving, shifting, reorganizing themselves in response to gravity and collisions and the subtle influences of Saturn's magnetic field. Flying through Saturn's rings, if you could, would be a surreal experience. From a distance, they look solid, but up close, you would see that they're made of individual chunks of ice, each one tumbling slowly as it orbits. In the densest parts of the rings, the B ring, the particles are packed closely together, and collisions are frequent, though usually gentle. In the gaps and the outer rings, the particles are more spread out, and you could travel for kilometers without seeing one. Sunlight would glint off the ice, reflecting in 1,000 directions, creating a glittering, shimmering field of light. Above you, or below, depending on your perspective, Saturn itself would loom, a vast golden sphere, its cloud bands slowly rotating, its shadow stretching across the rings like a dark curtain. The rings also create effects on Saturn itself. They cast shadows onto the planet's cloud tops, visible as dark bands that shift with the seasons as Saturn's tilt changes relative to the Sun, and they reflect sunlight back onto the planet, illuminating the night side slightly, a phenomenon that can be seen in images taken by spacecraft. The rings even rain down onto Saturn, a slow drizzle of ice particles that spiral inward and fall into the atmosphere, adding to the planet's water content and subtly affecting its chemistry. Saturn's rings are a reminder of the beauty and complexity that can arise from simple physical laws. Gravity, inertia, collisions, these basic forces, acting over millions of years, have created a structure that is both delicate and grand, a testament to the universe's ability to organize chaos into order. And yet, the rings are also a reminder of impermanence. They won't last forever. They're a fleeting feature, a snapshot of Saturn at this particular moment in its long history. In the deep future, they'll be gone, and Saturn will be a different planet, ringless perhaps, or with new rings formed from new moons, continuing the cycle of creation and destruction that defines the solar system. Before we move on from the rings, it's worth noting one more thing. The rings are not unique to Saturn. Jupiter, Uranus, and Neptune all have rings too, though theirs are much fainter and harder to see. Saturn's rings are by far the most spectacular, the most visible, the most extensive, but they're part of a broader pattern in the outer solar system. Ring systems seem to form naturally around large planets, wherever there are moons and debris and the right conditions for gravitational dynamics to play out. Saturn's rings may be the best example, the most beautiful, but they're not alone. They're part of a family, a category of phenomena that we're still learning to understand. And with that, we leave the rings behind, though not Saturn itself. There's still so much to see here. Moons that are worlds unto themselves, atmospheric phenomena that challenge our understanding, mysteries that Cassini uncovered and left for future missions to solve. But the rings, those glorious rings, are the first thing you notice when you look at Saturn, and they're the image that stays with you, shimmering faintly in the darkness, a crown of ice encircling a golden giant. Saturn's moons are a diverse and fascinating collection, and while there are dozens of them, one stands out above all the others, literally and figuratively. That moon is Titan, the second largest moon in the solar system, the only moon with a thick atmosphere, and one of the most Earth-like worlds we've ever discovered, despite being utterly alien in almost every way. Titan is strange, beautiful, and tantalizing, a place where lakes and rivers exist, where it rains from the sky, where the landscape is shaped by weather and erosion, just like on Earth. But the liquids on Titan are not water, they're hydrocarbons, methane and ethane, and the temperature on the surface is so cold that water ice is as hard as rock. Titan is larger than the planet Mercury, and if it orbited the Sun instead of Saturn, it would easily qualify as a planet in its own right. Its atmosphere is thicker than Earth's, with a surface pressure about 1.5 times what we experience at sea level. This atmosphere is mostly nitrogen, like Earth's, with a significant amount of methane and traces of other organic compounds. The methane is particularly important because it acts like water does on Earth, cycling through the atmosphere, condensing into clouds, falling as rain, collecting in lakes and seas, and evaporating back into the air. This methane cycle shapes Titan's surface in ways that are strikingly similar to the water cycle on Earth. From space, Titan is hidden beneath a thick, orange haze, a layer of smog made of complex organic molecules called tholins. This haze is so opaque that for a long time, we had no idea what Titan's surface looked like. It wasn't until the Cassini spacecraft arrived at Saturn in 2004, carrying with it the Huygens probe designed to land on Titan, that we finally got our first clear views of the surface. Cassini used infrared cameras and radar to peer through the haze, and what it found was astonishing. There were mountains, dunes, valleys, and, most remarkably, lakes. Actual lakes, liquid bodies sitting in basins on the surface, though filled with methane and ethane rather than water. The Huygens probe descended through Titan's atmosphere in January 2005, and the images it sent back during its descent and after landing were mesmerizing. The landscape looked eerily Earth-like in some ways, with rounded rocks, drainage channels, and a surface that seemed to be made of a mixture of ice and organic material. The rocks, if you can call them that, are likely water ice, frozen so hard in Titan's minus 180 degrees Celsius environment that they behave like stone. The surface appeared damp, possibly soaked with liquid methane just below a thin crust, and the atmosphere was calm. The light dim and orange filtered through the thick haze above. Titan's surface is geologically diverse. In the equatorial regions, there are vast fields of sand dunes stretching for hundreds of kilometers, made not of silica sand like on Earth, but of tiny grains of organic material, possibly tholins, blown into dunes by Titan's sluggish winds. These dunes are huge, some of them over 100 meters tall, and they follow patterns similar to dunes on Earth, shaped by the prevailing winds and the landscape they move across. In the polar regions, there are lakes and seas, some of them hundreds of kilometers across, filled with liquid methane and ethane. The largest of these, Kraken Mare, is bigger than the Caspian Sea on Earth, a vast body of liquid hydrocarbon sitting quietly under Titan's orange sky. These lakes are not stagnant. They change over time, their levels rising and falling with the seasons. Titan has seasons, just like Earth, because Saturn, and therefore Titan, is tilted on its axis. One Titan year is about 30 Earth years, and as Saturn moves around the Sun, different parts of Titan receive more or less sunlight, driving changes in temperature and weather. During Titan's northern summer, storms can form near the North Pole, and rain falls into the lakes, raising their levels. During winter, the methane evaporates and moves to the other hemisphere. Cassini watched these changes over the course of its mission, documenting the slow, stately march of the seasons on this distant moon. The idea that Titan has weather, that it rains, that clouds form and dissipate, is remarkable. It makes Titan the only other place in the solar system, besides Earth, where we know that liquids exist stably on the surface in significant quantities. This also makes Titan a place where life, though very different from life as we know it, might be possible. Not life based on water and carbon chemistry in the way Earth life is, but something stranger, life that uses liquid methane as a solvent, that operates at temperatures where water would be frozen solid. It's speculative, highly so, but it's not impossible, and that alone makes Titan one of the top targets in the search for life beyond Earth. Beneath Titan's icy crust, there's also evidence of a subsurface ocean, like Europa and several other moons in the outer solar system. This ocean is probably made of liquid water mixed with ammonia, and it's buried deep, 100 kilometers or more below the surface. It's kept liquid by heat from tidal forces and possibly from radioactive decay in Titan's core. This hidden ocean adds another layer of possibility to Titan's story, because where there's liquid water, even buried beneath ice, there's potential for life. Beyond Titan, Saturn has many other moons, each one interesting in its own way. There's Enceladus, a small, icy moon that has become one of the most exciting discoveries of recent years. Enceladus is geologically active, its south polar region covered with long parallel cracks called tiger stripes. From these cracks, geysers erupt, shooting plumes of water vapor and ice particles hundreds of kilometers into space. These plumes are evidence of a subsurface ocean, and they contain organic molecules, salts, and even hints of hydrothermal activity, suggesting that Enceladus has warm water vents on its ocean floor, similar to the vents on Earth that support rich ecosystems. The plumes from Enceladus feed Saturn's E-ring, creating a tenuous cloud of ice particles that stretches far beyond the Moon's orbit. Enceladus is tiny, only about 500 kilometers across, but it punches far above its weight in terms of scientific interest. Then there's Mimas, a small moon with a giant crater that makes it look eerily like the Death Star from Star Wars. The crater, called Herschel, is so large that the impact that created it nearly shattered the moon. There's Iapetus, a moon with a bizarre two-toned appearance, one hemisphere bright white, the other dark as coal, and a towering equatorial ridge that runs around much of its circumference like a seam. There's Rhea, Dione, Tethys, each one cratered and icy, each one telling a story of impacts and geological history. And there are dozens of smaller moons, irregular chunks of rock and ice, captured objects and fragments from past collisions, each one a piece of the puzzle that is the Saturnian system. Saturn's atmosphere, while less dramatic than Jupiter's, has its own mysteries. There's a hexagonal jet stream at the North Pole, a six-sided pattern that surrounds a massive storm at the pole itself. This hexagon is enormous, wide enough that several Earths could fit inside it, and it's remarkably stable, persisting for decades without significant change. Why it forms a hexagon instead of a circle is still not entirely understood, though it seems to be related to the interaction between different wind speeds and the dynamics of rotating fluids. It's one of those features that looks artificial, so geometric and precise, but it's entirely natural. A reminder that nature is capable of creating patterns that defy intuition. At the center of the hexagon, at the very North Pole, is a hurricane-like storm, a swirling vortex with an eye at the center, just like hurricanes on Earth. But this storm is hundreds of times larger, and unlike hurricanes on Earth, which are driven by warm ocean water, this storm is driven by Saturn's internal heat and the complex dynamics of its atmosphere. It's been raging for who knows how long, possibly since the planet formed, and it shows no signs of stopping. Saturn is also known for a phenomenon called ring rain, which we touched on earlier. The rings are slowly losing material, particles spiraling inward and falling into Saturn's atmosphere, pulled down by gravity and atmospheric drag. This rain is so constant and so significant that it may be shortening the lifespan of the rings, eroding them away over time. The particles burn up as they enter the atmosphere, adding water and organic material to Saturn's upper layers, subtly changing the planet's chemistry. It's a slow process, but over millions of years, it's enough to reshape both the rings and the planet. As we prepare to leave Saturn behind, it's worth pausing to appreciate what a rich and complex system this is. A planet with storms and seasons and a strange hexagonal jet stream, rings that shimmer with the light of billions of ice particles, moons that range from tiny, inert rocks to Titan, a world with lakes and rain and possibly even life, Enceladus with its hidden ocean and geysers. All of this orbiting a giant that generates its own heat, a world of gas and liquid and possibly a core of rock, all held together by gravity and spinning through the darkness at the edge of the sun's influence. Saturn is often called the jewel of the solar system, and it's easy to see why. There's a beauty here, a harmony, a sense that everything is in balance, even though we know that balance is temporary, that the rings are young and will eventually fade, that the moons are still evolving, that the planet itself is slowly contracting and cooling. But for now, in this moment, Saturn is magnificent, and it's a privilege to witness it, even if only through the eyes of spacecraft and the interpretations of scientists. We're not done with the gas giants yet. There are two more waiting for us farther out, colder, stranger, and in some ways even more mysterious than Jupiter and Saturn. These are the ice giants, Uranus and Neptune, worlds that stand at the very edge of the planetary system, where the sun's light is little more than a bright star, and the cold is so profound that even the gas giants we've seen so far seem warm by comparison. So take a breath. Let the image of Saturn and its rings linger in your mind for a moment longer, and then we'll continue, drifting outward, ever outward, toward the frozen giants that mark the boundary between the realm of planets and the vast empty expanse beyond. Moving farther from the Sun, past Saturn's orbit, we enter a realm of the solar system where everything becomes quieter, colder, and stranger still. The distances here are so vast that they challenge comprehension. Light from the Sun, which reaches Earth in just over 8 minutes, and Saturn in about an hour and 20 minutes, takes nearly 2.5 hours to reach Uranus. By the time it arrives, it's so faint that standing on Uranus, if such a thing were possible, the Sun would look like little more than a very bright star, providing almost no warmth, just a pale, distant glow. This is the realm of the ice giants, and the first one we encounter is Uranus, a planet so strange, so unlike anything else in the solar system, that it defies easy explanation. The most striking thing about Uranus, the feature that sets it apart from every other planet, is its tilt. Most planets spin like tops, their axes roughly perpendicular to the plane of their orbits around the Sun. Earth is tilted by about 23 degrees, which gives us our seasons. Saturn and Jupiter are tilted by similar amounts, but Uranus is tilted by 98 degrees. It's not just leaning, it's rolling, spinning on its side like a barrel tumbling through space. Its poles point almost directly toward and away from the Sun during the course of its orbit, which lasts 84 Earth years. This means that for about 42 years, one pole is bathed in continuous sunlight, while the other is plunged into continuous darkness. Then, as Uranus moves around the Sun, the situation reverses. No one knows for certain why Uranus is tilted like this. The most popular theory is that early in the solar system's history, Uranus was struck by a massive object, perhaps an Earth-sized protoplanet, in a collision so violent that it knocked the planet onto its side. Such an impact would have been catastrophic, reshaping the planet and possibly disrupting any moons it had at the time. If this theory is correct, it means Uranus carries the scar of an ancient collision, a reminder that the early solar system was a chaotic, violent place where planets were still finding their final configurations. Uranus itself is a pale blue-green sphere, its colour the result of methane in its upper atmosphere. Methane absorbs red light from the Sun and reflects blue and green light back into space, giving the planet its distinctive hue. But unlike Jupiter and Saturn, with their vivid cloud bands and swirling storms, Uranus appears almost featureless. Its atmosphere is calm, or at least it looks calm from a distance. There are faint bands visible in some images, and occasionally a storm or two can be seen, but for the most part, Uranus presents a serene, almost boring appearance. This lack of visible activity puzzled scientists for a long time. Why was Uranus so calm compared to the other gas giants? Part of the answer may lie in its internal structure. Uranus is classified as an ice giant, not a gas giant, though the distinction is subtle. Like Jupiter and Saturn, Uranus is made mostly of hydrogen and helium, but it also has a much larger proportion of heavier elements: water, methane, ammonia, things that we often call ices, even though they're not frozen solid in the planet's interior. These ices make up much of Uranus's bulk, and they may also explain why the planet doesn't generate as much internal heat as Jupiter or Saturn. Both of those planets radiate more energy than they receive from the Sun, but Uranus does not. It's almost in thermal equilibrium, meaning it emits about as much heat as it absorbs. This lack of internal heat may be why its atmosphere is so sluggish, why there are so few visible storms or dramatic weather systems, but that doesn't mean Uranus is inactive. When the Voyager 2 spacecraft flew past Uranus in 1986, it sent back images of a planet that seemed almost devoid of features, a smooth, pale disk with little to see. But more recent observations using the Hubble Space Telescope and ground-based instruments have revealed that Uranus's atmosphere is more active than it first appeared. Storms do form, especially near the poles, as the seasons change. Clouds drift across the planet, and winds, though slower than on Jupiter or Saturn, still whip through the upper atmosphere at hundreds of kilometers per hour. The calmness of Uranus may have been a fluke of timing, a result of Voyager arriving during a particularly quiet period in the planet's long, slow seasonal cycle. Uranus's tilt also creates some of the most extreme seasons in the solar system. Imagine living at one of Uranus's poles. For 42 years, the Sun never sets, circling the horizon in a slow, shallow arc, gradually climbing higher and then descending again. Then, as Uranus continues its orbit, the Sun sets, and for the next 42 years, your pole is in darkness, the only light coming from distant stars and the faint glow of the planet's rings and moons. The equator experiences something closer to normal day and night cycles. But even there, the geometry is strange, with the Sun rising and setting in unusual ways as the planet rolls through its orbit. Beneath the visible cloud tops, Uranus's atmosphere grows denser and hotter. As you descend, the pressure climbs, and the gases transition into liquids, creating a vast mantle of water, methane, and ammonia, possibly with some exotic chemistry occurring under the extreme conditions. This mantle makes up most of the planet's mass, and it's thought to be where Uranus's magnetic field is generated. But that magnetic field is odd too, another peculiarity of this strange planet. Unlike Earth or Jupiter, where the magnetic field is roughly aligned with the planet's rotation axis, Uranus's magnetic field is tilted by nearly 60 degrees relative to its spin axis, and it's offset from the planet's center. This gives Uranus a lopsided, asymmetrical magnetic field that wobbles as the planet rotates, creating a complex and constantly shifting magnetosphere. At the very center of Uranus, buried beneath thousands of kilometers of ice and gas, there may be a core of rock and metal, similar to Earth's core but much more massive. Or the core may be diffuse, mixed into the surrounding layers by billions of years of convection. Like so much about Uranus, the core is still a mystery, something we can infer from measurements of the planet's mass and gravity field, but which we've never directly observed. Uranus has rings too, though they're much fainter than Saturn's, and were only discovered in 1977, when astronomers noticed that a star's light dimmed briefly as Uranus passed in front of it. The star's light had been blocked by rings, thin, dark bands of material circling the planet. There are 13 known rings around Uranus, most of them narrow and made of dark, rocky particles rather than the bright ice that dominates Saturn's rings. These rings are puzzling. Where did they come from? Are they the remnants of shattered moons, or are they made of material that never coalesced into moons in the first place? No one is sure, but like everything about Uranus, they add to the planet's air of mystery. And then there are the moons. Uranus has 27 known moons, most of them small and icy, but 5 of them are large enough to be considered major moons. They're named after characters from the works of William Shakespeare and Alexander Pope, a departure from the tradition of using mythological names. There's Miranda, Ariel, Umbriel, Titania, and Oberon, each one distinct and intriguing. Miranda, the smallest of the 5, is perhaps the most bizarre. Its surface is a chaotic patchwork of terrains, with cliffs, grooves, and ridges that suggest the moon may have been shattered and reassembled multiple times by past collisions. One cliff on Miranda, called Verona Rupes, is the tallest known cliff in the solar system, dropping nearly 20 kilometers from top to bottom. If you could stand at the edge and look down, it would take you more than 10 minutes to fall to the bottom, drifting slowly in Miranda's weak gravity. Ariel and Umbriel are icy worlds, their surfaces scarred by craters, and in Ariel's case, crisscrossed by valleys and faults that suggest past geological activity. Titania and Oberon are the largest, both heavily cratered, both ancient, their surfaces unchanged for billions of years. These moons orbit Uranus in the plane of its equator, which means they also orbit at a steep angle to the plane of the solar system, a consequence of the planet's extreme tilt. Watching the moons of Uranus move is like watching a Ferris wheel slowly turning, the moons rising and falling as they circle the planet, their orbits carrying them above and below the plane of the ecliptic. Uranus is a planet of contrasts and contradictions. It's calm and featureless, yet it has storms and winds. It's an ice giant, yet it's made mostly of gas. It spins on its side, yet it has a stable system of rings and moons. Its magnetic field is lopsided, its seasons are extreme, and its interior is a mystery. In many ways, Uranus feels like the forgotten planet, overshadowed by the grandeur of Jupiter and Saturn, too distant and faint to capture the public imagination in the way Mars or Earth's moon do. But that obscurity is undeserved. Uranus is a world as complex and fascinating as any in the solar system, a place where the rules are different, where the familiar patterns of planetary behavior break down, and where every answer raises new questions. Standing on one of Uranus's moons, perhaps Miranda, looking out at the pale blue-green disk of the planet filling the sky, you would witness something no human has ever seen. The planet would hang there, enormous and serene, its faint rings circling it like halos, its other moons drifting slowly across the black backdrop of space. Above you, the sun would be a distant point of light, too far away to feel its warmth. The stars would be bright and clear, unobscured by any thick atmosphere, and you would be farther from home than almost anywhere else in the solar system, standing at the edge of what we think of as the realm of planets, looking outward toward the even more distant Neptune and the darkness beyond. Uranus is a reminder that the solar system still has secrets, that there are worlds out here we've barely begun to explore, places that challenge our understanding and force us to rethink what we thought we knew. It's a planet that doesn't fit neatly into our categories, a world that rolled its own path, literally, and that continues to intrigue and perplex anyone who takes the time to look closely. And as we prepare to move even farther out, to the last of the gas giants, it's worth remembering that Uranus, for all its strangeness, is still closer and more familiar than what's waiting for us next. Neptune, the final planet, the edge of the known solar system, is out there in the darkness, and it's time to drift toward it, to see what this distant, windswept world has to offer. But before we go, take one last look at Uranus. that pale blue sphere rolling through space, carrying its secrets beneath its calm exterior, a planet like no other, waiting patiently for the day when we return and look more closely. Farther out still, beyond even Uranus, at the very edge of what we traditionally call the planetary system, lies Neptune. It's the farthest planet from the Sun, a title it has held since 1999, when Pluto's elliptical orbit briefly brought it closer than Neptune, and Pluto was later reclassified as a dwarf planet. Neptune is almost 3 billion miles from the Sun, so distant that light takes more than 4 hours to reach it, and a year on Neptune lasts 165 Earth years. If you were born on Neptune, you would not live to see even half of a Neptunian year pass. It's a world of profound isolation, a blue giant hanging in the darkness, surrounded by faint rings and a collection of moons, one of which is among the most fascinating objects in the entire solar system. Neptune was not discovered by accident or by simply looking up at the sky. It was found through mathematics. In the mid-19th century, astronomers noticed that Uranus's orbit was not quite what it should be. Something was tugging on it, pulling it slightly off course, and the only explanation was that there must be another planet farther out, one whose gravity was affecting Uranus. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this unseen planet should be, and in 1846, astronomers pointed their telescopes at that spot in the sky, and there it was. Neptune. It was a triumph of mathematical prediction, proof that the laws of gravity worked even at the farthest reaches of the solar system. Neptune is similar to Uranus in many ways. It's an ice giant made mostly of hydrogen, helium, and ices like water, methane, and ammonia. It's about the same size as Uranus, though slightly smaller and denser, and like Uranus, it has a striking blue color, caused by methane in its atmosphere. But Neptune is different in one crucial respect. It's not calm. Where Uranus appears serene and almost featureless, Neptune is a world of violent storms and the fastest winds in the solar system. Winds on Neptune can reach speeds of over 2,000 kilometers per hour, more than twice the speed of the fastest winds on Jupiter and far faster than anything on Earth. Why Neptune is so much more active than Uranus, despite being colder and farther from the Sun, is one of the great mysteries of planetary science. The answer may lie in Neptune's internal heat. Unlike Uranus, which radiates almost as much heat as it receives, Neptune radiates more than twice as much energy as it gets from the Sun. This internal heat, left over from the planet's formation and possibly sustained by ongoing processes in its interior, drives powerful convection currents in the atmosphere, churning the gases and creating the storms and winds that define Neptune's appearance. The source of this heat is still debated. It may be the result of slow gravitational contraction as the planet compresses under its own weight. Or it may involve more exotic processes, chemical reactions or phase transitions deep in the interior that release energy over time. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit the planet, it sent back images of a world alive with activity. The most striking feature was the Great Dark Spot, a massive storm system roughly the size of Earth, located in the southern hemisphere. The Great Dark Spot was similar in some ways to Jupiter's Great Red Spot, a high-pressure system with winds swirling around its edges, but it was not as stable. By the time the Hubble Space Telescope turned its gaze toward Neptune a few years later, the Great Dark Spot had disappeared, replaced by other storms in different parts of the planet. These storms come and go, forming and dissipating over a period of years, driven by the turbulent dynamics of Neptune's atmosphere. There are also bright, wispy clouds high in Neptune's atmosphere, made of methane ice crystals that catch the sunlight and glow against the darker blue of the planet below. These clouds change quickly, sometimes forming and dispersing within a matter of hours, a sign of the dynamic nature of Neptune's weather. The planet's rapid rotation, which takes about 16 hours for one complete spin, combined with its internal heat, creates a complex and ever-changing atmospheric system that scientists are still working to understand. Beneath the visible clouds, Neptune's atmosphere transitions into a thick mantle of water, methane, and ammonia, much like Uranus. This mantle is thought to be in a state somewhere between liquid and solid, a slushy, high-pressure region where strange chemistry may be occurring. Some scientists have speculated that the pressure and temperature in Neptune's mantle might be high enough to break apart methane molecules, releasing carbon that then crystallizes into diamonds. If this is true, it means there could be a rain of diamonds deep within Neptune, gemstones falling through layers of exotic ices, eventually settling into a layer around the planet's core. It's a beautiful idea, though difficult to prove, and it's one of the many tantalizing mysteries that Neptune holds. At the center of Neptune, like Uranus, there's likely a core of rock and metal, perhaps as massive as Earth, but compressed to incredible densities. This core may be surrounded by the slushy mantle, with no clear boundary between the two, just a gradual transition from solid to liquid to gas as you move outward. Neptune's magnetic field, like Uranus's, is tilted and offset from the planet's center, creating a complex, asymmetrical field that wobbles as the planet rotates. This unusual magnetic field is thought to be generated not in the core, but in the mantle, where the movement of electrically conductive fluids creates currents that generate the field. Neptune has rings, though like Uranus, they're faint and difficult to see. There are 5 main rings, and they're made of dark, dusty particles that reflect very little light. Some of the rings have brighter sections called arcs, concentrations of material that are held in place by the gravitational influence of Neptune's moons. These arcs are puzzling because you would expect the material to spread out evenly around the ring over time, but something is preventing that from happening, keeping the arcs confined to specific locations. And then there are the moons. Neptune has 14 known moons, most of them small and irregular, but one of them stands out. Triton. Triton is the 7th largest moon in the solar system, and it's one of the coldest objects we've ever measured, with surface temperatures hovering around -235 degrees Celsius, just 38 degrees above absolute zero. Despite this extreme cold, Triton is geologically active, its surface covered with a mixture of frozen nitrogen, methane, and water ice, crisscrossed by ridges, valleys, and strange features called cantaloupe terrain, areas that look like the skin of a melon, with pits and bumps covering the landscape. Triton is also remarkable because it orbits Neptune backward in what's called a retrograde orbit. Most moons orbit in the same direction as their planet's rotation, but Triton goes the opposite way. This is a strong indication that Triton didn't form alongside Neptune, but was instead captured by the planet's gravity, probably from the Kuiper Belt, the region of icy objects beyond Neptune's orbit. If this is true, Triton is essentially a Kuiper Belt object, a distant cousin of Pluto that wandered too close to Neptune and was pulled into orbit. The capture process would have been violent. Triton's orbit would have been highly elliptical at first, and tidal forces from Neptune would have heated its interior, possibly melting much of it. Over time, the orbit circularized and Triton cooled, but the heating may have left a subsurface ocean hidden beneath the frozen crust. Even today, Triton shows signs of activity. Voyager 2 observed geysers erupting from Triton's surface, plumes of nitrogen gas and ice particles shooting several kilometers into space. These geysers are thought to be driven by a process similar to how geysers on Earth work, but powered by the weak sunlight that reaches Triton, which heats the subsurface nitrogen just enough to cause it to sublimate and burst through the ice. Triton's future is bleak, however. Its retrograde orbit means that it's slowly spiraling inward toward Neptune, pulled by tidal forces. Eventually, in perhaps a few billion years, Triton will cross what's called the Roche limit, the point at which Neptune's tidal forces will become strong enough to tear Triton apart. When that happens, the moon will be shredded, its material spreading out into a new ring system around Neptune, far more spectacular than the faint rings the planet has now. But that's a distant future, and for now, Triton remains, a captured world at the edge of the solar system, cold and active and strange. Neptune is a planet of extremes, the fastest winds, some of the coldest temperatures, a moon spiraling toward its doom, and an atmosphere that churns and roils despite receiving almost no heat from the distant sun. It's a place that challenges our understanding, that forces us to rethink what we thought we knew about planets and weather and geology. And it's a place that we've only visited once, briefly, a single flyby that gave us a tantalizing glimpse of what lies out there in the darkness. Standing on Triton, looking up at Neptune, you would see a sight that no human has ever witnessed. The planet would loom large in the sky, a brilliant blue sphere streaked with white clouds, its storms slowly churning across its face. The sun would be a distant star, bright enough to cast faint shadows, but providing no warmth, no comfort. Around you, the landscape would be alien, frozen and strange, with geysers hissing in the distance, their plumes rising silently into the airless sky. You would be at the very edge of the planetary system, billions of kilometers from Earth, surrounded by the darkness of space and the cold of a world that has never known warmth. Neptune is the last of the gas giants, the final stop on our journey through the outer solar system. Beyond it lies the Kuiper Belt, a vast ring of icy objects, remnants of the solar system's formation, and beyond that, the scattered disk and the Oort cloud, regions so distant that they blur the line between the solar system and interstellar space. But for now, Neptune marks the boundary, the edge of the realm where planets rule, and it's fitting that this edge is marked by a world so dynamic, so full of energy and mystery, despite its distance and its cold. As we prepare to turn inward again, to look not outward but downward into the hearts of these giants, it's worth pausing to appreciate what we've seen. 4 planets, each one unique, each one a world of storms and moons and mysteries. Jupiter, with its great red spot and its family of volcanic and oceanic moons. Saturn, with its glorious rings and Titan's lakes and Enceladus's geysers. Uranus, tilted and strange, rolling through space with its dark rings and fractured moons. And Neptune, windswept and distant, guarded by Triton, the captured moon that will one day become a ring. These are the gas giants, the sentinels of the outer solar system, and they've shaped our understanding of what planets can be. They've taught us that worlds don't need solid surfaces to be fascinating, that beauty can exist in the swirl of clouds and the shimmer of rings, and that even at the farthest reaches of the sun's domain, there's complexity, activity, and wonder. Now, we're going to delve deeper, not in space, but in understanding, as we explore what lies beneath the clouds of these giants, what secrets they hold in their cores, and what forces shape them into the magnificent worlds we see today. We've travelled across the outer solar system, drifting from one gas giant to the next, watching storms rage and moons glide past, admiring rings and marvelling at the sheer scale of these worlds. But now it's time to ask a deeper question, one that takes us not outward but inward, down through the layers of atmosphere, through the zones where gas becomes liquid and liquid becomes something even stranger. What lies beneath the clouds? What is hidden in the hearts of Jupiter, Saturn, Uranus, and Neptune? Because everything we've seen so far, all the swirling colours and towering storms, is just the surface. The real story of the gas giants is written in the depths, in places we've never seen and may never be able to visit, but which we can imagine and infer from the clues these planets give us. Start with Jupiter. We've talked about its atmosphere, about the great red spot and the bands of clouds that wrap around the planet. But descend past those clouds, and you enter a realm where the rules begin to change. At first, as you fall deeper, the atmosphere simply gets thicker and hotter. The pressure climbs, the temperature rises, and the gas becomes more and more compressed. There's no ground rushing up to meet you, no sudden transition from air to solid. Instead, the atmosphere just becomes denser and denser until, at a certain depth, it's no longer a gas at all. It's a liquid, but not like any liquid you've ever seen. This is liquid hydrogen, and it's everywhere, making up the bulk of Jupiter's interior. In this liquid hydrogen layer, the pressure is immense, millions of times the pressure at Earth's surface. The temperature is thousands of degrees, hot enough to melt rock, though there's no rock here, just hydrogen compressed under its own weight. You could think of this layer as an ocean, but it's an ocean without a surface, an ocean that extends for thousands of kilometers in every direction, seamlessly transitioning from the gaseous atmosphere above to the even stranger layers below. And as you go deeper, the pressure continues to climb until something extraordinary happens. The hydrogen undergoes a phase transition and it becomes metallic. Metallic hydrogen is one of the most exotic forms of matter in the solar system. Under the extreme pressures found deep within Jupiter, the electrons in hydrogen atoms are stripped away, and the atoms pack so closely together that they start to behave like a metal. This metallic hydrogen conducts electricity, it reflects light, and it flows like a liquid, but it's nothing like any metal you'd find on Earth. It exists only under conditions so extreme that we can barely replicate them in laboratories, and then only for fractions of a second. But in Jupiter's interior, metallic hydrogen is stable, and it makes up a significant fraction of the planet's mass. This metallic hydrogen layer is also where Jupiter's magnetic field is generated. As the planet rotates, the metallic hydrogen flows and swirls, creating electrical currents, and those currents generate a magnetic field, much like the dynamo in Earth's core generates our magnetic field. But Jupiter's magnetic field is far more powerful, and it extends far farther into space, creating a magnetosphere that dwarfs anything found around Earth. This magnetosphere traps charged particles from the solar wind, creating intense radiation belts that are hazardous to spacecraft and would be deadly to any astronaut who ventured too close. Deeper still, at the very center of Jupiter, there may be a core. This core, if it exists, is thought to be made of rock and metal, heavier elements that sank to the center during the planet's formation. But recent data from the Juno spacecraft suggests that this core might not be compact and well-defined. Instead, it may be diffuse, a region where rock and metal are mixed with hydrogen and helium, spread out over a large volume rather than concentrated in a small ball. This would imply that Jupiter's interior has been churned and mixed over the billions of years since the planet formed, perhaps by convection or by ancient impacts. Saturn's interior is probably similar to Jupiter's, though with some differences. Like Jupiter, Saturn has a thick atmosphere that transitions into liquid hydrogen, which then transitions into metallic hydrogen at greater depths. But Saturn is less massive than Jupiter, and the pressures in its interior are lower, which means the metallic hydrogen layer is smaller, and the transition happens at a greater depth relative to the planet's size. Saturn also has a lower proportion of helium than Jupiter, and some scientists think that helium is slowly raining out of the hydrogen in Saturn's interior, sinking toward the core and releasing energy as it falls. This process, called helium rain, might be one of the reasons Saturn radiates more heat than it receives from the Sun. At Saturn's core, like Jupiter's, there's probably a mixture of rock and ice, but again, the details are uncertain. The core might be compact, or it might be diffuse and mixed into the surrounding layers. One of the goals of future missions to Saturn is to study the planet's gravitational field in more detail, which would help us understand the structure of its interior and the nature of its core. Now, let's turn to Uranus and Neptune, the ice giants. These planets are different from Jupiter and Saturn in important ways. They're smaller, less massive, and they have much less hydrogen and helium relative to heavier elements. Instead, their interiors are dominated by what planetary scientists call ices. Though these ices are not frozen solid, they're water, methane, and ammonia compressed into a hot, dense state that's somewhere between liquid and solid, a kind of slushy, electrically conductive mantle that makes up most of the planet's mass. This icy mantle is where the magnetic fields of Uranus and Neptune are generated, but not in the same way as in Jupiter and Saturn. In Uranus and Neptune, the magnetic fields are tilted and offset from the planet's center, creating lopsided, asymmetrical fields that wobble as the planets rotate. This suggests that the magnetic field is generated not in a deep central dynamo, but in a shell-like region within the mantle, where convection currents in the conductive ices create electrical currents. Understanding exactly how this works is still an area of active research, and it's one of the reasons why scientists are eager to send more missions to the ice giants. Beneath the icy mantle, at the center of Uranus and Neptune, there's probably a core of rock and metal, similar in composition to Earth's core but much larger. This core might be solid, or it might be partially molten, kept hot by radioactive decay and by the pressure of the layers above. The exact size and composition of these cores are still uncertain, because we've never directly measured them, but models based on the planet's masses and gravitational fields suggest they could be as massive as several Earth masses. One of the most intriguing ideas about the interiors of Uranus and Neptune involves the behavior of carbon under extreme pressure. In the icy mantles where methane is broken apart by the heat and pressure, the carbon atoms might form diamonds. If the conditions are right, these diamonds could be raining down through the mantle, sinking toward the core like hailstones in a storm. This diamond rain might accumulate into layers or even oceans of liquid carbon at certain depths, creating a region unlike anything found on Earth. It's a speculative idea based on laboratory experiments and computer models, but it's consistent with what we know about the conditions inside these planets. And it's a vivid reminder that the gas giants are not just scaled-up versions of Earth. They're alien in the truest sense, places where the physics and chemistry are so different that even familiar materials behave in unfamiliar ways. The interiors of the gas giants are also dynamic. They're not static, frozen structures, but active, churning systems where heat and material are constantly moving. Convection currents carry hot material from deep in the interior up toward the surface, where it cools and sinks back down again. This convection drives the weather we see in the atmospheres, powering the winds and storms and redistributing heat around the planet. It also shapes the planet's evolution over time, slowly changing their structure and composition as lighter materials rise and heavier materials sink. Understanding the interiors of these planets is one of the great challenges in planetary science. We can't send probes into the depths of Jupiter or Saturn or Neptune. The pressure and temperature would destroy any spacecraft long before it reached the interesting regions. Instead, we have to rely on indirect methods, measuring the gravitational field to infer the distribution of mass, studying the magnetic field to understand what's generating it, observing the heat flow to see how much energy is coming from the interior, and using computer models to simulate the conditions inside these planets and see if the results match what we observe. Each new mission adds to our understanding. Galileo, which dropped a probe into Jupiter's atmosphere in 1995, gave us the first direct measurements of conditions below the cloud tops. Juno, which has been orbiting Jupiter since 2016, has measured the planet's gravitational and magnetic fields with unprecedented precision, revealing details about the interior that we couldn't have known before. Cassini did the same for Saturn, and future missions to Uranus and Neptune will hopefully do the same for the ice giants. But even with all this data, there's still so much we don't know. How big are the cores? Are they compact or diffuse? How much mixing has occurred in the interiors over billions of years? What exactly is the composition of the deep layers, and how do materials behave under those extreme conditions? These are questions that will take decades to answer, and they'll require not just new missions, but new technologies, new ways of studying planets from afar, and new theoretical insights into how matter behaves under conditions we can barely imagine. The interiors of the gas giants are hidden from us, locked away beneath thousands of kilometers of clouds and liquid and exotic phases of matter, but they're not unknowable. Every storm we watch, every measurement of gravity or magnetism, every observation of heat flow is a clue, a piece of the puzzle. And slowly, piece by piece, we're learning what these planets are made of, how they work, and what forces shaped them into the giants they are today. It's detective work on a planetary scale, and it's some of the most exciting and challenging science being done today. Imagining what it would be like to fall into one of these planets is a humbling exercise. There would be no moment of landing, no impact, no ground to catch you. You would just keep falling through layers that grow ever denser, ever hotter, ever more crushing, until you were compressed and incinerated, your atoms becoming part of the planet itself, mixed into the endless churning of its interior. It's a fate that no human will ever experience, thankfully, but it's a thought experiment that helps us appreciate the scale and strangeness of these worlds. They're not places we can ever truly visit, but they're places we can study, understand, and marvel at from afar. And as we finish this descent into the depths, it's time to pull back, to rise up from the crushing pressures and the exotic physics, and to ask a different set of questions. Not what these planets are, but how they came to be. How did the gas giants form? Why are they where they are? And what role did they play in shaping the solar system into the place we live in today? Those questions will take us back in time, billions of years, to a disk of gas and dust orbiting a young star, where the story of the gas giants first began. To understand the gas giants as they are today, we need to travel back in time, not just millions of years, but billions, to the very beginning of the solar system, when the sun was young and the planets had not yet formed. It's a story that begins in a cloud of gas and dust, drifting through space, cold and dark, until something disturbed it, perhaps the shockwave from a nearby supernova, perhaps just the slow collapse of gravity acting on the densest regions. Whatever the trigger, the cloud began to collapse, falling in on itself, spinning faster as it shrank, flattening into a disk with a growing concentration of mass at the center. That central mass would become the sun. As it grew, pulling in more and more material, the pressure and temperature at its core climbed until nuclear fusion ignited and the sun began to shine. But the sun didn't consume all the material in the cloud. A significant amount remained in the disk surrounding it, a swirling mixture of gas and dust that would, over the next few million years, coalesce into planets, moons, asteroids, and comets. This is the solar nebula, the birthplace of everything we see in the solar system today, and it's here that the gas giants began their existence. In the inner regions of the nebula, close to the young sun, it was hot. The sun's light and heat evaporated most of the volatile materials, water, methane, ammonia, leaving behind only rock and metal. These materials, though less abundant than the gases, were solid and could stick together when they collided, gradually building up into larger and larger objects. This is where the rocky planets, Mercury, Venus, Earth, and Mars, formed, growing slowly through a process called accretion, where small particles stuck together to form pebbles, pebbles stuck together to form boulders, and boulders stuck together to form planetesimals, objects kilometers or tens of kilometers across. But farther out, beyond what's called the frost line, it was cold enough for water and other volatiles to freeze into ice. This made a huge difference because ice was far more abundant than rock and metal. Beyond the frost line, there was simply more material to work with, and the planetesimals that formed there could grow much larger, much faster. This is where the gas giants were born. Jupiter formed first. In the outer regions of the solar nebula, a planetesimal grew quickly, pulling in ice and rock, building up mass until it reached a critical size, perhaps 10 or 15 times the mass of Earth. At that point, its gravity became strong enough to start pulling in the surrounding gas, the hydrogen and helium that made up most of the nebula, and once that process started, it ran away. The more gas the planet captured, the stronger its gravity became, and the more gas it could pull in. Within a relatively short time, perhaps a few 100,000 years, Jupiter had grown into a giant, sweeping up most of the gas in its vicinity and becoming the dominant object in the outer solar system, aside from the Sun itself. Saturn formed in a similar way, though perhaps a bit later and with less mass, leaving it smaller than Jupiter, but still enormous compared to the inner planets. Uranus and Neptune formed even farther out, where the density of material was lower and the process was slower. They managed to accumulate large cores of ice and rock, but by the time they were big enough to start capturing gas, much of the gas in the solar nebula had already been blown away by the young sun's intense solar wind, or had been captured by Jupiter and Saturn. This is why Uranus and Neptune have much less hydrogen and helium relative to their size, and why they're classified as ice giants rather than gas giants. But the story doesn't end with formation. Once the planets had formed, they didn't just sit quietly in their orbits. The early solar system was a chaotic place, full of interactions and collisions. The gas giants, with their immense gravity, influenced everything around them. They scattered smaller objects, flinging some into the inner solar system and ejecting others into the far reaches of space. They interacted with each other, their orbits shifting and changing as they exchanged angular momentum through gravitational resonances. One of the most dramatic ideas in planetary science is the Grand Tack hypothesis, which suggests that Jupiter didn't form where it is today, but farther out, and then migrated inward, moving closer to the Sun before reversing course and migrating back outward. This migration would have been driven by interactions with the gas in the solar nebula. As Jupiter moved through the disk, it would have pushed material around, creating a wake that exerted a gravitational pull on the planet, slowing it down and causing it to spiral inward. But then, as Saturn formed and began its own migration, the two planets fell into a resonance, and their combined gravitational influence reversed the inward drift, pushing both planets back outward to roughly where they are today. If the Grand Tack hypothesis is correct, it would explain several puzzling features of the solar system. It would explain why Mars is so small, because Jupiter's inward migration would have stirred up the asteroid belt and prevented material from accumulating into a larger planet in that region. It would explain why the inner solar system has relatively little mass compared to what you'd expect from models, and it would explain the distribution of water in the inner planets because Jupiter's migration would have scattered icy bodies inward, delivering water to Earth and the other rocky worlds. Another influential idea is the NICE model, named after the city in France where it was developed. The The NICE model suggests that the gas giants formed in more compact orbits than they have today, and that a later period of instability, perhaps hundreds of millions of years after the planets formed, caused their orbits to shift dramatically. In this scenario, the planet's gravitational interactions with a massive disk of icy planetesimals beyond Neptune's orbit caused their orbits to change. Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. This migration scattered the icy planetesimals throughout the solar system, sending some crashing into the inner planets, possibly causing the Late Heavy Bombardment, a period around 4 billion years ago when the inner solar system was subjected to intense impacts. The NICE model also explains some features of the outer solar system, like the Kuiper Belt, the region of icy objects beyond Neptune's orbit. The outward migration of Neptune would have scattered objects in this region, creating the structure we see today, with some objects in stable orbits and others in more chaotic, scattered trajectories. Pluto, for example, is in a resonance with Neptune, orbiting the Sun twice for every 3 orbits of Neptune, a configuration that keeps the two objects from ever colliding despite their orbits crossing. These migration theories are still being refined and debated, but they highlight an important point. The gas giants didn't just form and sit still. They shaped the solar system, sculpting the orbits of smaller objects, delivering water and organic materials to the inner planets, and creating the structure we see today. Without the gas giants, the solar system would look very different. There might not be a stable asteroid belt. Earth might not have the water that makes life possible. The outer solar system might be full of large planets instead of the sparse collection of icy worlds we observe. The gas giants also continue to influence the solar system today. Jupiter, with its massive gravity, acts as a shield, deflecting or capturing many of the comets and asteroids that would otherwise make their way into the inner solar system. Some scientists call Jupiter the solar system's vacuum cleaner, though that's not entirely accurate because Jupiter also sends some objects inward. But on balance, its gravitational influence has probably reduced the number of impacts on Earth over the history of the solar system, making the development of life somewhat less hazardous. The gas giants have also taught us about how planetary systems form in general. Over the past few decades, astronomers have discovered thousands of planets around other stars, exoplanets, and many of them are gas giants. Some of these exoplanets orbit very close to their stars, so close that they're heated to thousands of degrees, earning them the name hot Jupiters. These planets couldn't have formed where they are because it's too hot for gas to accumulate there. They must have formed farther out and then migrated inward, just as Jupiter might have done in our own solar system's early history. Studying our own gas giants helps us understand these distant worlds. By figuring out how Jupiter, Saturn, Uranus, and Neptune formed and evolved, we gain insights into the processes that shape planetary systems everywhere. And by studying exoplanets, we learn more about the range of possibilities, the different paths that planetary systems can take, and the factors that determine whether a system ends up with gas giants in the outer reaches like ours, or with hot Jupiters hugging their stars, or with something entirely different. The formation of the gas giants was not a predetermined process. It depended on the conditions in the solar nebula, the timing of events, the interactions between growing planets, and a fair amount of chance. If things had been slightly different, if Jupiter had formed a bit later or in a slightly different location, if the nebula had dispersed sooner or lingered longer, the solar system might look very different. We might have more gas giants, or fewer. Jupiter might have migrated all the way into the inner solar system, becoming a hot Jupiter and possibly preventing Earth from forming at all, or Jupiter might never have formed, leaving the outer solar system empty of large planets and changing the entire history of the solar system. Understanding how the gas giants formed, how they migrated, and how they shaped the solar system is one of the central goals of planetary science. It's a story written in the orbits of planets and asteroids, in the composition of comets and meteorites, in the craters on moons and the rings around planets. It's a story that's still being pieced together, with each new mission and each new discovery adding another chapter, another detail, another clue to how our solar system came to be. As we step back from this deep history, from the swirling disk of the solar nebula and the chaotic early years when planets were still finding their places, it's worth reflecting on what the gas giants represent. They are not just objects to be studied, not just collections of gas and ice and exotic matter. They are witnesses to the birth of the solar system, survivors of a violent and transformative era, and architects of the world we inhabit. They are the reason Earth exists as it does, with its water and its stable orbit and its relative safety from impacts. They are, in a very real sense, part of our story, part of the long chain of events that led to this moment, here and now, where you're listening to these words and imagining worlds billions of kilometers away. We've travelled far tonight, drifting through the outer solar system, from Jupiter with its storms and volcanic moons, to Saturn with its glorious rings and hidden oceans, to Uranus tilted and strange, and finally to Neptune with its howling winds and captured moon. We've descended into the depths of these giants, imagining layers of metallic hydrogen and oceans of diamond, and we've travelled back in time to watch them form from a disk of gas and dust, shaping the solar system into the place we call home. It's been a long journey, and now, as we prepare to bring it to a close, it's time to ask what all of this means, not just for science, but for us, for the way we see the universe, and for the future of exploration. The gas giants are reminders of scale. They're so large, so massive, so unlike the world we live on, that they challenge our ability to comprehend them. When we say Jupiter could hold 1,000 Earths, or that Saturn's rings stretch farther than the distance from Earth to the Moon, or that winds on Neptune move at 2,000 kilometers per hour, these are just numbers. But if you pause and really try to imagine what those numbers mean, to picture the sheer size and power of these worlds, it becomes almost overwhelming. And that's okay. The universe is overwhelming. It's vast beyond comprehension, and the gas giants are just a tiny part of it. 4 planets orbiting one star among hundreds of billions of stars in our galaxy alone. But the gas giants are also reminders of beauty. There's something profoundly aesthetic about Saturn's rings, about the swirling bands of Jupiter, about the deep blue of Uranus and Neptune. These are not human constructs. No one designed them for our enjoyment. They exist because of physics and chemistry and the relentless working of natural law, and yet they are beautiful in a way that transcends utility or function. Beauty, it seems, is woven into the fabric of the universe, appearing in places no human eye has ever seen, and existing whether we're there to appreciate it or not. The gas giants are also testaments to our curiosity. For most of human history, they were just points of light in the sky, wandering slowly against the fixed stars, mysterious and unreachable. But we didn't stop at wondering. We built telescopes, we developed theories, we sent spacecraft across billions of kilometers of empty space to see these worlds up close, to measure their magnetic fields and sample their atmospheres and photograph their moons. And in doing so, we transformed them from mysteries into places, real and complex and full of stories. This drive to explore, to understand, to push the boundaries of what we know is one of the most remarkable things about our species. It doesn't always serve an obvious practical purpose. Knowing about the rings of Saturn or the volcanoes of Io won't pay your bills or cure disease or solve the problems we face here on Earth. But it does something else. It expands our sense of what's possible. It reminds us that we live in a universe far stranger and more wonderful than we could ever have imagined. And it gives us perspective, a sense of our place in the grand scheme of things, which can be humbling but also liberating. Looking ahead, the exploration of the gas giants is far from over. There are missions being planned and built right now that will return to these worlds and their moons. NASA's Europa Clipper, set to launch in the coming years, will orbit Jupiter and make dozens of close flybys of Europa, studying its icy shell and the ocean beneath, searching for signs that it might be habitable. Another mission, the Dragonfly rotorcraft, will fly to Titan in the 2030s, hopping from place to place on the surface, exploring the lakes and dunes and searching for the building blocks of life. There are also proposals to send orbiters to Uranus and Neptune to study these neglected ice giants in detail and unlock the secrets of their interiors and atmospheres. Each of these missions will answer some questions and raise new ones. That's how science works. Every discovery opens new doors, new mysteries, new frontiers to explore. And the gas giants, for all we've learned about them, still have plenty of secrets left. We still don't fully understand their interiors, or how their magnetic fields are generated, or why their atmospheres behave the way they do. We don't know if there's life in Europa's ocean, or Enceladus's vents, or Titan's lakes. We don't know exactly how the planets formed, or how much they migrated, or what role they played in delivering water to Earth. These are questions for the future, for the scientists and engineers and explorers explorers who will build the next generation of spacecraft and instruments, who will analyze the data and develop the theories and push our understanding ever forward. And they're questions for everyone, because the exploration of space is not just for specialists. It's a collective human endeavor, something we do together, funded by societies, celebrated by cultures, and shared through images and stories and moments of wonder that belong to all of us. If there's one thing the gas giants teach us, it's humility. They remind us that Earth, for all its importance to us, is just one small world among many. It's not the center of the solar system, not the largest or the most dramatic or the most powerful. It's a rocky ball orbiting an ordinary star, and most of the solar system's mass is locked up in the sun and the gas giants, not in the terrestrial planets. And yet, despite this, Earth is special in one crucial way. It's home. It's where life emerged, where consciousness arose, where we built our civilizations and our cultures and our dreams of exploring the stars. The gas giants also teach us resilience. These worlds have existed for more than 4 billion years, weathering impacts and storms and the slow grinding of geological time. They've changed, yes. Jupiter's great red spot is shrinking. Saturn's rings are young and may one day disappear. Uranus was knocked on its side by a massive collision. Neptune's Triton is spiraling toward its doom, but through all of this, the gas giants endure, patient and vast, orbiting the sun in their slow, stately dance, indifferent to the passage of time. And finally, the gas giants teach us wonder. There's something almost magical about the idea of a world made entirely of gas, of rings that shimmer in the sunlight, of moons with underground oceans and geysers that shoot into space. These are things that sound like science fiction, but they're real. They're out there right now, turning in the darkness, waiting for us to come back and look more closely. And the more we learn about them, the more wondrous they become, because the reality is always stranger and more beautiful than anything we could have invented. So here we are, at the end of this journey, having travelled billions of kilometres in our minds, having seen storms that could swallow Earth and moons that might harbour life, having descended into the crushing depths of exotic matter and risen back up to watch rings sparkle in the distant sunlight. It's been a long night, a slow drift through the outer solar system, and if you've made it this far, thank you. Thank you for your curiosity, for your patience, for your willingness to imagine places you'll never visit, and to wonder about questions that may take generations to answer. The gas giants are out there right now, just as they were when we started this journey, just as they were yesterday and will be tomorrow, and for billions of years to come. Jupiter is churning, Saturn is shimmering, Uranus is rolling, Neptune is howling. Their moons are orbiting, their rings are spinning, and the universe is continuing its endless unfold, indifferent to whether anyone is watching. But we are watching. We're looking up, building telescopes, sending spacecraft, asking questions, and piecing together the story of these distant worlds. And in doing so, we're writing our own story, the story of a species that looked at the night sky and decided to understand it, that built machines to explore the solar system and minds to interpret what those machines found. It's a story that's still being written, and the gas giants are a big part of it, not because they're close or familiar, but because they're vast and strange and beautiful, and because they remind us that the universe is full of wonders waiting to be discovered. So rest now. Let the images of these giant worlds drift through your thoughts, the swirling clouds, the glittering rings, the hidden oceans. Let yourself imagine standing on Europa's ice, or drifting through Saturn's rings, or watching a storm rage on Neptune from the frozen surface of Triton. These are places that exist, that are real, even if you'll never touch them, and they're part of your universe, part of the vast cosmic inheritance that belongs to all of us, simply by virtue of being here, now, in this time and place, looking outward and asking what else is out there. The gas giants have much more to teach us. Their story is not finished, and neither is ours. There will be more missions, more discoveries, more moments of wonder as we continue to explore the outer solar system and beyond. But for tonight, this is enough. We've seen what school never quite had time to teach, and we've let ourselves slow down enough to really appreciate it, to feel the scale and the beauty and the strangeness of these worlds. Sleep well, traveller. The gas giants will still be there tomorrow, patient and vast, turning in the darkness, waiting for the next curious mind to look up and wonder.